Now let's consider a circuit like this, where this is the capacitor, this is the resistor, and we have two sources which I'll consider to be identical. I'm not going to write that down, but these are identical sources. And we have a toggle switch here that could toggle us from here to here. Now when the switch is toggled over here, it's open here, so that this source has no effect on the circuit since it doesn't have a closed loop around the circuit. And when it's toggled over here, this one is taken out of the circuit. So that when toggled over here, the current in the circuit, the voltage will tend to push the current around this way. And when toggled over here, the voltage will tend to push the current around this way. Now what's going to happen is if we close a switch to enable this current, we're going to build up positive charge on the positive side of the capacitor, negative charge on the negative side. That'll go on for a while, then we'll toggle the switch over here, and what's going to happen? We have positive charge here that's looking at the negative terminal of the battery over here, so it's going to be pulled off rather strongly. Of course, the resistor is going to mitigate that. And a positive charge here that's articulating with the negative side of the capacitor, and that's going to tend to pull negative charge back over here, which is going to tend to neutralize the charge on the capacitor and then reverse it, putting positive charge on this side and negative charge on this side. Now let me clarify one common misconception about circuits, just to digress into the physics just a little bit. And I'm going to kind of wave my hands on this. Obviously, I can't develop the whole theory of electrical conduction in a differential equations course. But the fact that one side of the capacitor doesn't have a resistance between it and the source doesn't really have any effect. The effect of the resistance here is actually to concentrate the electric field gradient into the resistor, so that you have an electric field that's a result of this source and the capacitor, and it kind of gets concentrated mostly into the resistor in a way that I can't really, I could make it specific, but it would take a while, so that negative charge isn't pulled over here any more quickly than positive charge would be pulled over here, or with the switch in this position. The resistor doesn't slow the flow of positive charge over here any more than it slows the flow of negative charge over here. The position of the circuit elements in a series circuit ultimately makes no difference. Again, for reasons that I really can't take time to explain here. In any case, it's fairly easy to see what happens in an intuitive way. If we close the switch and have this switch toggled over here, and we have an initially uncharged capacitor, we're going to start exponentially approaching the equilibrium charge. Now, that's going to continue until we toggle the switch and reverse the source. So at this point, and at this time here on the t-axis, we toggle the switch, and now the charge tends to approach negative Q equilibrium, because of course we have the source reversed here. And that's going to continue until we toggle the switch again, come back up here, etc. Notice that the charge doesn't reach zero at the same time we reverse the switch. After reversing the switch, there is some time delay while the charge falls back to zero. So the capacitor becomes uncharged, not at the instant we throw the switch or toggle the switch, but at some later instant. That's an important property of these circuits that comes out of the solutions to the equations, so that when we interpret those solutions, hopefully we'll have some insight into what's going on. So I've made that note that Q reaches zero after the source reverses, and then Q approaches negative Q equilibrium with the same time constant as before. That means that the half-life of our approach to equilibrium to this equilibrium is the same as the half-life of our approach to this equilibrium. I probably didn't do a really good job of drawing it that way. You might think about how you would draw that more accurately to reflect this condition. In any case, we toggle the switch again, and now we approach up here, and that's going to continue. And we're always going to have the zero charge at some point after we toggle the switch. Now, if we toggle the switch sooner, we're going to cut this buildup off sooner. And then if we toggle it the other way and then toggle it back sooner than we did before, we're going to have less time to fall back toward this equilibrium position. And we're going to end up with a smaller amplitude in our looking for the word to describe this thing. I wanted to say sawtooth, but a sawtooth is linear between peaks. Anyhow, in this alternating, non-sinusoidally alternating charge. If we toggle with a lower frequency, we're going to get up closer to the equilibrium charge and come down closer to the negative equilibrium charge. So we're going to have a greater amplitude in our charge versus time relationship. Now, if we use a source with a smoothly varying voltage, and let's say a sinusoidally varying voltage, and you've seen how we use sine functions for oscillatory systems, then our source could be of the form V max times the sine of omega t. We have our capacitance, we have our resistance, and the voltage of the source will be a nice sine wave. If we close a switch on this system with the capacitor initially uncharged, then the voltage of the source is going to build a little bit, and that's going to tend to cause charge to flow faster and faster in the circuit, so that the charge will build, and it will build at an increasing rate. We'll have kind of a concave up region of the graph until the charge gets large enough to start really opposing the buildup. And then the charge is going to relax, and eventually the rate of buildup is going to become zero before the charge reverses. Now, where is it that the buildup of charge peaks? Well, the charge is going to continue to build as long as the source has a positive voltage. So any positive voltage is going to tend to move. Well, actually, I'm wrong about that, and I'm going to have to stop there and fix that. And I'm not going to do that until the next clip, because I'm going to have to redo a lot of this stuff, and I want to do it right. The problem is that as the charge builds, the voltage in the capacitor builds. So the charge begins to fall when the voltage on the capacitor is equal to the voltage of the source. So that's going to occur before the voltage of the source falls back to zero. So pretty much this picture is invalid. I kind of knew that before, and I should have looked a little more closely at it before I started talking about this. Since we haven't gone to that point, I think there's no harm done. We'll fix that, and we'll continue on in the next clip.